Hello, good morning. It's great to see a full room for day two ground floor at BSides' 10th conference in Las Vegas. Few announcements as usual before we begin. Just a reminder, we are live streaming, cell phones off. If you have questions, come to the microphone. As always, we'd like to thank our sponsors, especially our Inner Circle sponsors, Critical Stack and Valimail, as well as stellar sponsors BlackBerry, Microsoft, and the Paranoids. Our talk is on hidden networks pivoting. Please welcome Tomer Zait and Nimrod Levy.
Okay, thank you very much. Like you said, my name is Tomer Zait, and this is Nimrod Levy. We'll show you the hidden network pivoting using the redefining DNS rebinding attack. We call the tool Retinal, but you will see all the concept behind it. So my name is Tomer Zait. I'm a security researcher at F5 Networks. I'm a CTF enthusiast. You can see some CTFs. I'm also a CTF developer in BSidesLV and also OASP-IL and OASP Global. I'm an open source developer, and that's it to talk about me. Now, Nimrod.
Hey everyone, my name is Nimrod Levy. I am the CTO and co-founder at Scorpiones. I'm here to talk to you about DNS rebinding automation and a tool that we developed called Retinal. In my daily work, I perform research on various technologies, conduct red team operations, and give back to the community by developing open source tools. So, how did this research begin? As a part of our community contribution, we are the developers at BSidesLV CTF. And last year, we developed a challenge called Can You Bypass the SOAP? The feedback from this, the challenge was based in DNS rebinding vulnerability, of course, and the feedback was the exploitation process is complex. So Tomer and I then think how we can make this process simplify and build the Retinal tool. Then we presented the tool at BSidesLV and Black Hat Asia last year, and we will present it again in the upcoming Black Hat USA and of course here. Before we talk about the Retinal, we need to first understand some basic concepts. The first concept we discuss will be same origin policy, followed by cross-origin resource sharing, and then some DNS caching basics. So, same origin policy is a browser-enforced restrictions that prevent your domain from accessing resources that are not compatible with same origin policy checks. Same origin policy checks ensure that your domain has the same schema, hostname, and port. If one of the check fails, your request will be blocked by the same origin policy. In this example, you can see that evil.com is trying to retrieve the Lucifer file. The request will be allowed because there is not violation for the same origin policy. But if evil.com will try to get a resource from good.com, the request will be blocked because of that evil.com is not allowed to get access to good.com. But what if evil.com actually won't get access to good.com? We can do that. In this case, the cross-origin resource sharing comes to the rescue. Cross-origin resource sharing is a mechanism that uses HTTP headers to tell the browser how to deal with outgoing AJAX requests to a different origin. In this example, you can see that evil.com is trying to get access to good.com, that the request will be permitted because you can see that there is header called access control allow origin that permit access to evil.com. In some situations, the browser will trigger a pre-flight request. If order to try, it will try to send the simple request. A pre-flight request is a HTTP request that issued prior to a main course HTTP headers under certain conditions, such as method with a special method, put, delete, etc., etc., etc. The browser first send an option request to ensure whether evil.com can perform operations with good.com. And if is not, the request will be blocked. If it is, the next request will be the actual request with all the parameters. In this example, you can see that evil.com is trying to access good.com with certain conditions. You can see that by the mentioned headers, etc., there is rules that you can read in Google. But unfortunately, the request will be blocked because good.com does not permit access to evil.com. For that, the request will be rejected by the browser and will not send the actual requests. Now, let's talk a little bit about DNS and DNS cache. Please take a look at the following DNS response packet. You can see that the hostname is translation. The hostname translation is directed to the localhost address. You can see also that the time to leave is 152 seconds. It means that the local DNS cache will store the record for 152 seconds. Now, let's see how it looks on a Windows machine. First of all, we will ping our server, which will trigger a DNS request. The DNS response will be translated to the localhost address. Then, we will update the record to 133.7 IP with our DNS server. It will be used with the Cloudflare for this example. But you can see that there is still 24 seconds left before the cache expires. Okay. When the cache expires, hold on. You wait for the command. Okay. When the cache expires, you can see that the local DNS cache is empty. Now, we will send a new DNS request by sending a ping. This, in turn, will trigger, of course, a new DNS request, and the DNS response will resolve the new IP and map the hostname to the 133.7 IP. Now, let's see how it works. The victim computer send a request to evil.com, which goes to our DNS server. The DNS server will resolve our malicious server IP. Next, the browser will issue a GET request to the resolved server IP and execute the following malicious JavaScript code. The JavaScript code will call itself until the evil.com HTML title is changed. Once the title is changed, the attacker knows that what has happened. The attacker knows that the rebinding process was successful. When the script calls itself, our DNS server will change the IP assignment to another internal IP. And once the local DNS cache is renewed and populated with the new IP, the attacker has access to the resource and can send requests to the host and take and compromise internal assets. Tamer.
So let's talk about the area before Retinal. what happened with DNS rebinding, because it's a 10-year-old attack that is still exists in the wild. So before Retinal, we'll see what happened to the DNS rebinding tools. So for the DNS rebinding tools to work, you needed to gain information about the victim. You can't attack using DNS rebinding without knowing the IP addresses that you are going to attack. You needed to use scripts, different scripts, to scan the network, to understand that those ports are to find the hosts, and to understand that those ports that you found in the scanning process are HTTP ports, because if it's not, you cannot attack using DNS rebinding. And then, after you have all this information, you needed to create scripts in advance to attack those internal assets. You need to use scripts that attack the router or the internal application, but it will be only using to attack one application at a time. You cannot create something that will be granular and will work on every application in the world. So let's talk about the disadvantages of this process. So you need information about the user, about the internal assets. This information is really hard to get. You really need to find a way to get the internal IP addresses, to find what applications they have, because if you don't know the applications you are going to attack, you cannot use those automatic scripts to find the attack, the attack for you. Okay, and now it's hard to configure. Those tools are really hard to configure if they have a configuration. Not all the tools has a configuration. And if it has a configuration, sometimes it's a code configuration. So you need to understand how to code in order to configure the application. The scanners are mostly slow because they use only timeout attacks to find the internal assets, to understand if this IP exist or not exist, and never knows if the port is open and the port is each HTTP port before it starts the rebinding process. There's no victim management for most of the tools. So if there's no victim management, you will forget some of the victims, and you will not be able to gain information from those victims and to execute the attacks, like the SQL injections on the internal applications. And let's don't say SQL injection, because with the old tools, you cannot use SQL injection on an application that you don't know. If it's an internal application that someone just developed on his local machine, you cannot attack this application using SQL injection. So the payloads are limited. It's just for known tools, for known assets, for known applications. So they're really limited for scripts that the community created. And you cannot attack manually. If you want to just see the application in your own eyes and to understand, okay, there's a basic authentication mechanism. Maybe I will use this basic authentication. I will brute force this basic authentication mechanism. I will find the username and password, and then will just get an access to the application. Even if it's Tomcat, it's really hard to do those scripts, to create those scripts manually using JavaScript and then use the DNS rebinding tools. And you can't use automatic tools like SQL map. But we want to use SQL map to gain access to the database and then drop all the tables and get the information, to dump all the tables and get the information about the users and passwords and everything in the database. So we can't do it in the old tools. So this is the thing that Retinal will give you. it will give you the option to use all those features that you could not use in the old tools in a new manner. So let's see how it works. This is the automatic process of Retinal. Retinal will get internal IP address. For now, it won't work on the version of Chrome 75 and so on, because they fixed it. Now you cannot get internal IP address using WebRTC, but we're still using another techniques. We will add them onto the next version that will fuzz between IP addresses that we know that could be in the internal network to understand if this network exists, that there's an IP address like 122.168.11. And if this IP address exists, that means that we can scan this network to the 255 IP addresses and then find the internal assets, find the ports, and exploit the applications. So we will scan for the internal hosts. Then, after we found the internal hosts, we will try to scan for open HTTP ports. We use our own JavaScript reconnaissance scripts. Some of them use timeouts. Some of them use events in the DOM elements. But they're all very accurate. We check it a lot before we publish the code in GitHub, of course. And it will bypass browser limitations. So in your browsers, you cannot use script that will just show you that there's basic authentication behind the scenes, behind the asset. Like when you send requests to a web page, you either send the credentials in advance, or you just send the credentials in the URL. But in the newer version of the browsers, you cannot use the all the mechanism of sending the username and password inside the URL, but only one function allows it, and it's the regular AJAX request. So we use it to send an AJAX request with bad credentials, and then we know that there's a basic authentication behind the scenes that showed us that those credentials are wrong. But in the next time, you will be able to insert the right credentials. So we automate the whole. It will automate the whole DNS rebinding process inside the Retinal script. It will tunnel through victims to the internal network. That means that you can actually surf on the internal network asset, like the router. You just click on a link, and you see the router like it was in the DMZ. It's not, but we have our own scripts and our own features that allows us to just surf the web in the internal network like it was in the DMZ. Then you will be able to manage everything, all the attacks and all the victims in one single page with all their assets. So let's talk about Retinal and see how it works. So this is the architecture of Retinal. You can see we have the core application. The core application is the malicious web application. It's also the command and control center that you can see, the attacker can see all the assets of the victims, but it also attacks the client. So the client open a web application, just open a link. In our demo, we will see it will be solitaire game, because game is less longer, and as long as people are in a specific web page, you will be able to gain more information and to attack more assets. Okay, so they click on a link, they just forget about it. The link is then translated to the core application. The core application understands that the DNS rebinding process should be started, and it will talk to the DNS to change the IP address, like you saw in Nimrod's demo. So then after the DNS address changed, you will get back to the core application, and the attacker will be able to use the core application to get access to the internal assets. So how we really create a proxy from the user that serves to the web, from the victim browser. That's what I will talk about now. So we have a client JavaScript proxy, but how it works, you cannot just send requests to the victim browser. You just can't. Even if you know the IP address, the victim browser is still the victim browser. You can't send requests directly from the victim browser, from the attacker to the internal assets. But what you can do, you can use a malicious app in the middle that will translate the web page to the attacker from the victim browser. And this is one of the best features we have on Retinal. It will allow you also to send requests like post, put, delete, patch, and every other request that you could not do in the old tools. So now I'll talk about how it works. You will see everything in the code. Like I said, it's all open source. So to do so, to be able to gain information, to gain access to the internal web applications, the victim need to click on the link, and on this link there's a malicious web application, and the malicious web application just create using JavaScript a WebSocket connection with the malicious web application. It's still the same web application with WebSocket and also with the HTTP. Now, the attacker send requests to the internal, the malicious web application with the internal web application information. Like here you can see the IP address, but you can still see it's the same domain. It's still evil.com, but the subdomain will have information about the victim, like the victim ID and the victim IP address and the victim port, because in one victim we'll have many IP addresses because there's a full internal network behind it, and also there's lots of ports because in one host you will have many ports, and maybe some of them are HTTP ports. So you need this information in order to get the right response from the right web application. I did not write it, but to talk with many assets in the same web application, we created iframe. It's really ordered to get the information from as many web applications as we can, and to do it asynchronously. So we have iframes, and we connect to those iframes with web messaging. So now we have the mechanism of how we can send requests, but let's see the real request. So we send the request to the malicious web application, but how we can get the information we need from the web application, the internal web application in the victim browser network, from the malicious web application. So the malicious web application has a responses dictionary, and it will save the response object we're using Node.js. It is possible to create a global response object that will have a key value paired responses. And also we can just create a timeout mechanism to set a timeout when the response is timed out. Just if we waited for 10 seconds and the response never came, we can just set a timeout mechanism that will respond with timeout. So now the malicious web application will send a push message to the WebSocket in the victim browser with a unique identifier and the whole request information. Here I just showed you the URI. and the method, but you will see also data and another good information about, like, you will see the credentials for basic authentication, and you will see also the headers, and new customized headers that we want to send in the request from the browser to the internal assets that already rebinded using Retinal and the DNS rebinding. Now, after the victim browser responded with another push of a message using WebSocket to the malicious web application, you will see the same identifier, but now you will see the headers of the response and also the data, the body of the response that will come back to the user. And now the attacker, the malicious web application, finds the right response and just respond using send function and returning the response with all the headers, even where basic authentication headers, and with all the information and with all the body of the response to the attacker. Even if it's binary files, the attacker will be still be able to download those binary files using the same technique. So, as I said, you can find the Retinal code, source code, here in GitHub/Retinal. And now I will talk about the easy part. Why is it so easy? It seems so hard to set up all these things. Like, you need a DNS server, and you need the core application, and you need the database, and you need everything. But it's not that hard. You can just use Docker to Docker compose app -d, because we want it to be with the daemon. And then you will have the DNS server, the core application, and also the database in the same server. Then you need to register a domain. So you need a domain. We chose this Freedom because Freedom has just free domains. And now when you have the domain, you can just insert the name server. So the name server is actually the web application that you had. But you say, okay, I don't have a subdomain called ns.retinal.co.il or .ml or whatever domain you have. Yes, you don't have, but for that, you can use glue records. So with glue records, you will have like an internal host file. You create an IP that will be translated to subdomain, though it will not go to the DNS server at all. It will just be translated immediately. So that way, you will be able to create the name servers, and then you will be able to use them. So now you just need to set your admin credentials, and you're good to go. So now I will show the demo. I hope the demo is longer. I think I done it a little bit fast. So I will show the demo, then you'll ask your questions. I will try to pray to the demo gods because it's a live demo. And last time I prayed, it didn't work. So maybe now, after I sacrifice Nimrod, everything will be okay. So let's see. This is the internal web. This is Retinal. This is the web application of Retinal. I know I can say there's no now it's duplicate. Okay, so this is Retinal. You can see Retinal here, and you can see that somebody tried to connect to Retinal. I don't know why. It's not a good idea, people. It's really, if you don't want your internal network to be ours, don't do it. Okay, good choice. So now I will connect to the RDP again because it's all messy out there. Okay, so this is their remote desktop, and we'll open Retinal link. It's just a solitaire game. You can see it's a regular solitaire game, a JavaScript solitaire. I hope the internet works. If not, I will use my my phone for that. Let's see. Yes, I'm connected. I will just, in advance, try to use this. I also have a recorded demo because I don't trust the demo gods. But I want to show it in real time. So let's use the phone instead. Okay, it works. Here is the solitaire. And now it started the whole Retinal process. So now it scanned for the hosts. You can see it out here. 1 second. It's a little bit bigger than it was when I tried this demo. Okay, so you can see it's scanning the network. There's an iframe. And you will see, oh, it's already started. Let's see. The refresh. I will just stop the organized group iframes so we can see the whole requests going. Here's the ping. Here's the pool. Here is the requests. You can see request going. So now it's scanning for ports. I will tell you why I chose Solitaire. It's a really funny story. I thought about using Pac-Man or Mario, but then I thought, but I can lose. And I'm a gamer, and it won't look good if I lose in Mario. And so I chose the game that I don't need to do anything in order to play. So I just make it stay that way, and that's it. And now it's scanning for the hosts. We'll see when it will be finished. For a few seconds. Here's the hosts. Now you see the popped up basic authentication. This is a mechanism that we created in order to get responses from basic authentication hosts. If there's a host with a port that behind this port there's a web application with basic authentication, we still need to gain information that it is a web application with basic authentication. So we have some ways in order to get this knowledge. So we found all the hosts, and now we searched for the ports. And as you can see, there's ports in the local host, and there's ports in other assets like 8080 in another IP address inside the network, and 80 on another assets, still 80 on another asset. And now we'll see what the attackers see when all this information get to the attacker. So let's see. I will just refresh this page because the internet wasn't that good. Okay, now the DNS rebinding process finished. So we can just see everything in the attacker webpage, the command and control. I'll do it for another minute, and if it won't work, I will just show the video that we created before the the convention. Oh my God, that's slow. Okay. Oh my God. Okay, so here's the attacker perspective. So here we have lots of information that we got from the user. We have the assets that we rebinded. And of course, the internet just disconnected us. Holy cow. So I'll try to do it before it will disconnect us once more. So now what we can do is we can just go to those assets, just explore those assets, and see the web applications behind it. So here we can see that inside the user, the victim, had an internal web application, a simple HTTP server with Python. And in this simple HTTP servers, he had a directory listening. So now we can just download binary files from the internal web application just by clicking on a link. That's it. We just see the web application and we can download those binary files. And now I see that it's really slow. So I will just go to the recorded demo. I am sorry, because I don't want you to wait for eternity. It's like you want to pee and just need to hold it. Oh, cool. The demo guys really don't like me. I will just reopen the presentation. Okay, let's go to the demo. Screw you once again, demo gods. I won. Okay, so now we'll see the same thing, but with the recorded demo. I'm sorry, it's too slow and I can't handle it. My heart is really pumping right now. So here's the demo. We just scan for the hosts and for the ports in the internal assets of the victim. So the victim opened a solitaire game, and now we're just creating filters for the logs of the Retinal, because Retinal is in debug mode, and it will almost ever be in debug mode, because it's still in the development stage. It's still beta or alpha or whatever. It's an open source application. Who cares? So now we'll get the hosts, the internal hosts in the internal network, as you can see. And after that, you will see the internal ports. It will scan for the internal ports. This is a short process because we already have all the hosts and we have a configured ports. And now it will rebind to every port you can see in the internal ports that it found. So it will start the rebinding process right now. And we should see the whole new hosts that was created with a random string for every internal host and port and user victim. We should see it right now. You can just fast forward. Okay, you can see it right there. I'll rewind because maybe you missed it. Here's all the rebinded internal hosts and ports. And now we just have the command and control center. It's the same application that the user used in order to get the attack started. And as you can see, we just clicked on the binary file and we saw the response. Here we will see another web application inside the network. I just want to show you before I finish the presentation. You can see here that every subdomain has information about the user, so you can automate using your tools. You just need the cookie, the Retinal cookie, because we are still security people, so we don't want anybody to gain access to the internal web applications of another victim. We just want it to be ours. So there's a security cookie. So this is the IP address. You will use the IP address in every Retinal link. This is the port, and this is the ID, the unique identifier that every user has on the local storage. So now you will see that we can actually use basic authentication like the application was in the internet, in the DMZ. So we can just use Tomcat, find Tomcat in the internal network. Now use Tomcat to, oh, okay, sorry about that. Just insert the credentials to Tomcat using basic authentication in our own attacker web browser. And we have control on the management of Tomcat. But it's not enough. We can just use another techniques like using an old exploit that uses the put method in order to create new pages in Tomcat, and we just have a web shell. So this is another demo of what we can do using just Retinal in a Retin. Okay, so we use the shell to help you. And now you will see that we can also use Retinal with automatic tools like SQL map. So we'll see the DVWA application. It's a vulnerable web application with lots of vulnerabilities. We'll check the SQL injection vulnerability here in DVWA. We'll just set user ID to 1. We'll take the response because we still need the cookie, the Retinal cookie. We'll save it aside. You can see the whole response here with the cookie. We'll open CMD, or here's PowerShell, although I had PowerShell, but still, it was the faster option. Now we just execute the SQL map command with the request file, and it will find that we have MySQL database here. Of course, we'll tell it, yes, it's MySQL, don't try another database. And now it will find the attack vector, generic union. So still, yes. Don't waste your time. We know the attack vector. And you should see right now that it started to get the attack started, the SQL injection attack, and it knows that the ID parameter is vulnerable, and now it found the right amount of columns. And it found the user table. And if we click one more time, you can see the whole database dumped in front of our eyes. So you can use automatic tools in the internal assets of someone just using Retinal. It was never existed in the wild, not officially, of course. I think we are not the first ones to create those tools, but it's so simple that anybody could use DNS rebinding attack everywhere without knowing anything about the victim. So I want to thank Max Rank for the logo, the awesome logo. I also have 2 stickers if you will have time. I can give it to you. We're the fastest people here. More than 2 stickers. I have 4 stickers. So thanks to Max. And also Dima Belsky for the UI. That's the only way that the UI will look like a UI and not like a drawing of a 10-year-old boy, if I created the UI. So thanks, Dima. And now we have time for questions. Anyone?
How do you pick the subnets to scan? And could you make that threaded so it scans a little faster? It looks like 1 a second per IP.
So it's multi-threaded. Yes, it's multi-threaded. We cannot use more than 8 threads in Chrome. The problem is that Chrome has a limitation of threads. He has its own queue, and this queue will expire some of the requests if it's not executed in the right time. So we used a library we created called JS pool. Like in Python pool, you have pool of threads. You tell it how many threads you want. So here we use 10 threads. Maybe in Firefox we can use more threads, but it still doesn't work on Firefox. And we just create the requests, and it's with promises, so we know the request executed and returned. So we can populate with another request and another request and another request. So it's really fast. It's not faster than a regular scan because you don't have this queue that Chrome has and you don't have this problem. We tried to bypass this problem using web workers and iframes and stuff. It didn't work, so it's still using this library we created called JSpool. You can just check it out. It's in the same project, and it's still really fast. It's something like 1 minute, the whole DNS rebinding process for an entire internal network. Between 1 to 2 minutes. It's the faster you will get in the internet, believe me. I saw many tools. Okay, another question?
This was difficult to see from the back. Were any of the services you exploited on the internal network SSL enabled?
No. Of course, it's one of the ways you can protect from DNS rebinding exploitation. So if you want to protect against DNS rebinding, SSL, if you don't have a bot that has SSL termination off or something, like you can just check that this bot will not verify. Like Selenium do it by default for most of the web browsers because they don't want to check the SSL because, when you create an internal web application, the SSL is just custom-built SSL self-signed SSL certificate. So you can just send requests to those web applications and you will not see the errors that Chrome shows when it checks the SSL and it fails. But in other type of clients, like the regular clients, the real people, not bots, you will not be able to send requests to the internal assets that use SSL, because when you change the host name, and even this change will make the SSL fail, and then you will not be able to get the response. So this is one of the protection mechanism you can use. You can also create one host for every web application, and if you use another host, it will just send an error. So,
Thank you. Very cool.
okay. Another question?
Thank you very much. I had a question from the defense side.
Sure.
On the host system, would you see just Chrome doing all this, or would you see like SQL Map spawning up, or other like Nmap or other tools that you would use with that tool?
You will see Chrome, but if your SQL Map uses the SQL Map, no, you will see Chrome. You cannot change the user agent from JavaScript, so you just see Chrome.
So you just see Chrome doing all
Yeah.
these things?
Yeah.
And you just probably see like Chrome creating the new connections and stuff like that?
Yes.
Interesting. Okay.
Using Ajax.
Cool.
So just for clarification, I saw you had the internal DNS server running within your malware, but wouldn't a DNS server just be able to filter a request that comes back from an RFC 1918 address? Wouldn't that be a way to kind of stop the rebind attack, or is that something you did with your internal DNS server?
Yes, you're right. You can just filter those requests. There are few ways to bypass it, like you ordering the priority of the request. So one request, one DNS, the one address will get a lower priority than the other, and then it will just mingle between those requests. But still, I don't think it's a good idea, because you have an internal assets, and those internal assets has an internal IP addresses. So I don't think you can really use this mechanism to protect against DNS rebinding attack. When you have internal web application inside your network, they will use the same IP addresses. So it's not really a good idea to do it, unless you have a customized DNS server, and you can just customize the internal web applications to have the same DNS but with subdomains of the same DNS. It will be much easier, to protect. Another question? Okay, so thank you.
Thank you.